All right, hello everyone. My name is Kevin Pluchter. I am a master's student at Carnegie Mellon University, working under the guidance of Sebastian Scheer, who's the head of the Air Lab. So today I'll be presenting my work on precision UAV landing in unstructured environments. So the goal of that, you guys can see the image in the top right corner. You kind of see some lines and arrows going up. This is a drone that is taken off from a small block, and we would like that drone to come back down and precisely land where it took off from. And we'd also like it to do this in an unstructured environment. And when I say this, I mean an environment where I have not placed a structured object to enable the drone to assist in the landing process, so something like a landing pattern. And from this result, you can see we have successfully taken off and landed on the block. And doing so, we follow a similar trajectory from takeoff on the way back down to successfully complete this task. So throughout the talk, I'll go over the background of similar or other approaches towards a similar problem, as well as the challenges of this problem, my approach, as well as the results and conclusions. So for background, for the task of precision landing, there are two primary ways you can go about doing this. One is using the drone's state estimation, which generally on low-cost drones, this will drift over time, and low-cost GPSs tend to have fairly high inaccuracies. So you won't get very precise and accurate landing in areas. The next way is by using a known landing pattern. So you've designed this landing pattern. The drone knows what this landing pattern looks like, can search for that, and use that to estimate its position error. So we would like to do it in environments such as shown here, where just on a patch of grass that you decided to go fly your drone and wanted to return home, or on a patio, multiple environments, and have it more generalized to not needing that landing pattern. Additionally, the landing pattern methods generally run into issues with the field of view. So this has been worked around in different papers by using two separate cameras, one that has a wider field of view for once you're lower to the ground or a different angle, as well as one that has a better focus for higher up. Another approach is by designing your landing pattern specifically to have features that can be seen at a high altitude, as well as features that can be seen at a low altitude. The final background isn't a method for precision landing, or it's actually a technique that inspired my method called visual teach and repeat. This method will have an operator drive a robot along a set path that they would like it to follow. It records images along this path as a teach pass, and then uses this to localize along the path to accurately follow that path. So the challenges of the problem that I've presented is that we want to identify the location to land, which is where you took off from, without any previously placed markers in that spot, and as well as the field of view issues as you come into landing, seeing the ground in which you took off from. Our contributions is a safe precision landing algorithm in unstructured environments, and experimental results in various environments, including grass, turf, rocky environments, and tile, and then experimental comparison of cameras to help resolve or better solve the field of view issue seen in this problem. So now with the background set up, I will go into my approach. So first, the physical system. There are three primary portions to it: a downward-facing fisheye camera, a downward-facing laser rangefinder to measure the altitude, as well as an onboard IMU GPS EKF state estimate, which came on board our Autel X-Star drone, and we just used that. So more or less the current standard drone state estimation systems. Then we use also two primary assumptions. One is a flat ground plane, which we believe to be a fairly reasonable assumption, as most areas from which you're taking off need to be flat in order to have the drone stably placed down that you can take off from, as well as there's fairly low scene change, which with most drones having a battery life of about 20 minutes, we don't foresee the scene changing too much. But we also did run some experiments to see how well the algorithm worked with scene change. So to go into this a little bit, I'll first start off with a bit of a video showing the algorithm working. So once again, we have our problem of landing the drone accurately. And our key result is that it follows along a similar path back to the takeoff position. And now here, our approach, we have a pilot, which was me, taking the drone off from this block. I avoid the tree, and during this process, the drone will be actively recording images during the takeoff. Then, during the landing for our experiments, we have an arbitrary offset, which is over the tree in this case. We will find features and match them from the current image to images from takeoff, and use that to calculate a relative position error and get a velocity command. It will then descend and use the images from takeoff to follow along a similar path back to the initial position, which is, you can see the velocity commands being given on the right, and the drone landing back on the block. So for the procedure, or our approach, there are two primary parts, the takeoff procedure, as well as the landing procedure. The takeoff procedure, as I mentioned, at our experiments, we have a pilot take off the drone, and in this, images are recorded as well as height data and data from the state estimation for the roll and pitch of the drone. And these are recorded for later use during the landing, and they are recorded based on the height of the drone. So as the drone ascends, it will record these images in set intervals. We use a higher rate at the ground as the field of view is changing at a more drastic rate, and then a slower rate once you're higher up in the air. Then, once the takeoff is finished, which we defined as 7.5 meters for our experiments, this can be a tuned parameter for different variable environments. The orb features are extracted from all of the images and saved, as well as their descriptors for later use. Now for the landing position, the idea for this precision landing algorithm is the final portion of the landing. So it'll come back approximately to the position where it landed or took off from, and then from there it will correct the rest of the error. So starting from there, it returns to the final takeoff position, approximately, and based on the current height of the drone with the laser rangefinder, selects the nearest image from takeoff that was below it. From this, it will estimate an error, which for that, we use the roll and pitch recorded, as well as the current roll and pitch estimated, to correct for the angle of the feature points. Then, with our ground plane assumption, and the height known, we can project these points onto the ground plane below us and estimate a 2D rigid body transform with Ransack. And this gives us a relative position error that doesn't have any scale ambiguity. Using this, we generate a velocity command that is sent to the drone while it is descending. As it descends, when it passes below the image from takeoff that it's comparing to, it will transition to the next image that was recorded during takeoff that is nearest below it. So to quickly wrap up, there's a lot of steps here. So this is more of a holistic procedure. Our two primary sensors are the fisheye camera and the laser rangefinder, which then during takeoff, images from the fisheye camera are undistorted. And recorded based on their height. After this is finished, you extract the features. Then during the landing, you once again undistort the fisheye camera, extract features, which we use orb features, select the image from takeoff, find features which you can see here an example of. This is landing over grass. After that, you compensate for the rotation of the drone, the roll and pitch, and project it into 3D and estimate the rigid body transform, and generate velocity commands for the drone to follow to come back to its initial position. Now that we've covered through the approach, I will delve into our results and conclusions. So we ran two primary experiments to get our results. One was a basic landing experiment. We had a pilot take the drone off to over 7.5 meters, move it with an arbitrary offset, and then start the landing procedure. We did this in two methods, our proposed method with our precision landing algorithm, and the second was using the onboard IMU GPS state estimate. And that way we could have a a baseline comparison for our results. Secondly, we also attached a pinhole camera to the drone to record images along with the fisheye camera. So all the data that was used in the algorithm was taken or recorded during the takeoff and landing. And then offline, we can compare how well the fisheye camera produces or estimates rigid body transformation as compared to the pinhole camera, and see this is kind of how we validated our decision in helping with field of view, particularly throughout the landing process. The second experiment we ran was a scene change experiment. So although we do assume that our scene does not change very much, we were curious to see how robust it was to major features being moved in the image or removed from the image. So that was the second experiment, which we ran 3 particular trials, and I'll explain that once I get around to that slide. So for the landing test results, first, the chart on the right is the results from the pinhole and fisheye camera testing results. The x-axis is the height range in buckets, so from 10 meters on the far right down to the ground on the far left. And the y-axis is the percentage of bad matches, which we decided this whenever Ransack could not come to a consensus on the rigid body transform. You can see this, the pinhole camera struggles more than the fisheye, particularly at the start of the landing and the end of the landing, which we believe is due to the field of view issue when the start is further from the initial point, that the images do not overlap enough, as well as the final point when the field of view is not large enough to cover the ground, that it's, so the images no longer overlap. So then for the bottom chart, the first 4 rows are results from our proposed method, and the last 2 are from trials ran with the state estimation on board. Our accuracy and precision are both far better than the state estimation on board. We also recorded wind speed from a nearby airport to see how well our algorithm worked in windy environments. And on the days of testing, there was greater wind speed and max gusts than on the days for the precision landing algorithm as compared to the state estimation, and it still worked better. For the scene change experiments, there's 3 primary experiments ran. You see in the images, short, long, and mid long. So that is based on, our experiment was, we have this van here, and we took off the drone from varying distances from the van. After takeoff was completed, we shifted the van by a set distance, and then started the landing procedure to see how well it performed. So for, I guess, more qualitative results, the red box shows approximately where the drone took off from in these trials. For short and medium, it took off from 4 feet away from the ambulance or van, and then it moved 16 feet away. For short long, it started from 4 feet away, moved to 41 feet. Medium long from 16 feet to 41 feet. And now the yellow box shows primarily where the drone tended to land. And then this is reflected in the chart shown. For short medium, the drone tended to have a fairly large error in the final position. For short long and mid long, the error was lower with a few outliers that had very large error. So this, you can see here, the landing position is fairly similar on the shadow produced by the van from where it took off from in short medium. And then in the other experiments, this is also where the drone landed for the outliers. So this showed us basically, if you have a strong set of features in the scene and those are shifted to a new location that are still within the image, this will tend to pull the drone to land in those positions. So it is a fairly predictable failure. Then for the other cases, the strong feature set was removed from the image or pushed far enough out that it then weighted less in the position error, and the drone was able to land fairly accurately still with the remaining features. In conclusion, we believe that we have produced a fairly accurate, or an accurate precision landing algorithm for unstructured environments, which also based on looking around other papers is the first. And with 40 centimeter average accuracy across varying environments, it's robust to wind disturbances and varying environments. The fisheye lens provides more information for field of view without degrading the capability of estimating error, and is robust to features being removed. And then I believe I'm running out of time, but the future work you can discuss with me after the talk or during the panel session. So thank you for your time, and I can take any questions now.
Thank you, Kevin.